How we do. Hopefully it works for us. So well, first of all, I hope everybody's well. The last section in chapter 9 is where we're going to start. This section starts out with a picture of a birthday cake with 4 candles on it. The proportion or ratio of candles to birthday cake is 4 to 1. Probably familiar with the colon symbol from your mathematic days, and chemistry uses ratios and proportions as well. There's 2 laws of proportions we need to be concerned about, and those 2 laws came out of early work measuring masses of compounds, and also ultimately gave us the tools we needed to write formulas and name compounds. The first law is the law of definite proportions, and the second one is the law of multiple proportions. There's something going on here with those proportions. The law of definite proportions was developed in the late 1700s by Joseph Louis Proust, who's a French chemist, and he, like many others, were measuring samples of chemicals and decomposing them and trying to figure out what the heck they were made of. What he found is that the masses of the elements that make up a compound always stay in the same proportions no matter what size sample you might have. Back in the early days, this was also called the law of definite composition, and also known as Proust's law. This is a really bizarre picture from your book of a piece of blue jean in a beaker of water. You'll notice that the fabric looks darker in the water because that's what happens when things get wet with water. Water obeys the law of definite proportions, and when it's analyzed, every sample of water has a mass ratio of oxygen to hydrogen at 8 to 1. Now, the actual masses for moles worth of these elements are 16 grams for oxygen and 2 grams for hydrogen, but you know from your mathematics days that you need to reduce a fraction, simplify a fraction into its simplest form, and that would be 8 to 1. Please notice this is not the atomic ratio that's in the chemical formula for water. This was done measuring masses because we hadn't even decided that matter was made of atoms at this point. This next picture shows another piece of blue jean denim stuck in hydrogen peroxide. You might know that hydrogen peroxide is used to highlight your hair, or used in changing the color of your hair. It's a natural bleaching agent, so when you put the jeans into that, you'll notice they lose their color, but it also obeys the law of definite proportions. In this case, however, the mass ratio of oxygen to hydrogen is always 16 to 1, 32 grams oxygen for every 2 grams of hydrogen. And again, right, got to reduce to the simplest form, per 1. Again, that's not the atomic ratio, not the number of atoms of hydrogen to the number of atoms of oxygen, but there's something going on here. These ratios, as I just stated earlier, are the masses, so grams, not number of atoms. However, some brilliant person figured out that different masses could be explained if matter was made of atoms, and that each element's atoms were a different size or mass. And of course, the brilliant person that figured out matter was made of atoms and brought it to modern chemists was our old friend John Dalton. John Dalton, the English school teacher in Manchester, England, stated that if you have the same 2 elements forming 2 different compounds, the masses of the elements are going to work out to be small whole number ratios of grams. So there's a consistent pattern with whatever size sample you have of the mass of one element to the mass of another. So if you look at water and look at hydrogen peroxide, pretty quickly you look at their chemical formulas. They're both liquids at room temperature. They're both clear and colorless. They have very different characteristics. However, they're the same two elements, simply in different proportions. So if they're in different or multiple ratios or proportions, you're going to get different results or characteristics. There's an analogy of how the letters of the alphabet, there's only 26 of them, but there's thousands, probably millions of words, right? Same kind of thing with our 118 elements making thousands, millions of compounds. I prefer to do my talking and thinking with cooking, so you've probably made brownies and cake from boxes before. Some of you probably made them from scratch and know that they have the same basic ingredients: flour, sugar, cocoa powder, eggs, butter. Those same simple ingredients used in different proportions are going to give you very different results. This is really evident in the weird way that nitrogen and oxygen go together. Remember that they don't follow the ionic charge pattern that we learned at the beginning of the semester. When two nonmetals go together, they can do all sorts of weird things like coordinate covalent bonds and double bonds and triple bonds and have resonance and all that other stuff we learned about. So if you look at this one, you'll see that the first compound, nitrogen monoxide, 14 to 16, 14 grams of nitrogen for every 16 grams of oxygen. And then we go to the next one, nitrogen dioxide, 14 and 32. Well, pretty easily you can see they have the same mass of nitrogen, and that the masses of the oxygen are simply multiples of 16. And you look across the pattern, you see multiples of nitrogen. 14 times 2, of course, is 28. And then look at this one on the end, crazy, crazy. 2 14s and 5 times 16 would get you that 2 to 5 atomic ratio of this compound. That's my vicious dog Daisy in the background. Law of multiple proportions, of course, was also worked out with carbon monoxide and carbon dioxide. Today, it's super obvious to us that this is the case. Of course, makes sense if you already have the concept of atoms. At Dalton's time and Proust's time, it wasn't quite that obvious. Here's another diagram from your textbook. Compound X, compound Y, they're both composed of the same elements A and B. However, the proportion or the ratio of element A to element B is different in the two of them. Notice that 5 plus 2 is 7, 10 plus 2 is 12. 5 divided by 2 is a different ratio than 10 divided by 2. That's only 5 to 1. A couple things to remind you about: ratios are simply fractions. We also tag them with the word proportion. If you see a denominator with a slash, a per something, and just units after the slash mark, like dollars per pound or dollars per gallon, you're supposed to insert the numerical value of 1 in your denominator. For example, gas is $3.39 a gallon, or it was. And when you make that into a fraction, you have to remember the dollars per gallon. Okay? Units are super important for this next several things that we're going to be doing, and you're going to need your calculator. This is a good video. Hank talks as fast as usual. The link is on the document for you to access it. I highly recommend you watching it. Here's a sample problem. If you've got your calculator handy, that will be useful. Lead forms 2 compounds with oxygen. One has 2.98 grams of lead to 0.461 grams of oxygen. The other has 9.89 grams of lead to 0.763 grams of oxygen. Are they the same? Well, we already know lead forms 2 different charged ions, cations, and that causes it then to react differently with oxygen. This is how they figured it out. If you imagine that the lead to oxygen ratio is a fraction. You divide the first two sets of numbers and you get 6.46 per 1. Do the same with the second set of numbers, 12.96 per 1. Obviously, they're not the same. So which one has the lowest mass ratio, lowest whole number mass ratio? These aren't whole numbers. That doesn't do us a lot of good. Well, the 1 is for the oxygen. So what we do next is we just go ahead and take the bigger number and divide it by the smaller number. You'll see it basically comes out 2 to 1. Slightly, little tiny bit, hundredths place of error. That's easy to explain away with experimental procedures. So 2 to 1, it has twice as much. This is twice as much lead to oxygen in it. The last part of this section has you going through a flow chart on naming compounds. We did this pretty extensively. I don't really think we need to review it, but if you feel like you could use a review, take a peek at these pages. It's a yes-no dichotomous screening key. How are you going to name things? Notice that the Q is in the cation place. The R is some make-believe anion, or first element, second element, and then of course X and Y are subscripts. And it just helps you to divide. Is it a metal? Is it in group A, etc. Copper CuSO4 is a compound you can deduce from there. Copper is not in group A, so you know that there has to be a Roman numeral because it's a transition metal. SO4, of course, is sulfate, and this is actually a hydrated compound. I'll do a demonstration for you later in the week. I'm taking this pretty blue substance and heating it up. It'll turn into a white, boring looking substance until you put water back in it, and we'll talk about what that has to do with percent composition later too. There's also guidelines on how to write the chemical formulas. Again, some of you may benefit from reviewing this. Probably all of us could. Ide ending says it's a binary compound. Ite or ate probably has a polyatomic ion that has oxygen in it as the anion. If there's prefixes in the name, it's got to have 2 non-metals. And if there's a Roman numeral in the name, that's telling you the charge on the metal cation. And again, they have the flow chart that you can look at on your own. The one question I really want you to think about at the end here, the law of definite proportion states that in a sample of any chemical compound, the elements are always in the same proportion by and hopefully you know its mass. The last 2 questions, you can pause it here, are asking you questions based on naming. And you can pause and read this one here. And that's it, and I hope you're all well and healthy and safe. Take care till next time.